Hey guys, today we're going to finish up our last topic for this chapter of linear regressions. We are going to do two more chapters for this unit. So chapter 8, you could of course look in the book if you want to know, but chapter 8 is going to be over regression wisdom. So just some things that we can, just going into further into depth about regression. And then chapter 9, which is pretty cool, I think so at least, is going to be re-expressing data, just like straightening up scatter plots. Now we're going to be able to straighten up scatter plots so that we can re-express the data so it's linear and then create a linear model. And then how do we interpret those linear models with the re-expressed regression equation? So anyway, today's topic is going to be the last one for this chapter here, and basically what we're talking about is a tale of two regressions. So if we change the order, so for instance, if we're going from protein to predict fat, can we create another linear regression that goes from fat to predict protein? And what happens when we switch the location of the variables from our explanatory variable to our response variable and vice versa? So for instance, let's just do a quick review here. So here we have our scatter plot. This is a standardized scatter plot because we're dealing with z-scores. Z-scores of protein by z-scores of fat here. All of the, remember the correlation coefficient is calculated by first finding the by graphing out these standardized stat plot by basically converting all of the data points to z-scores. Now all those points are converted to z-scores by taking the observation minus the mean, which is the average for average protein and average fat, and then dividing it by the standard deviation for the protein. Then over here for the z-scores for the y terms for the fat, we take the actual fat content per item minus the mean for the fat content, and then we divide by the standard deviation for the fat content. Okay, so we actually are basically standardizing these so that we can compare them to each other, comparing apples to oranges in this case, by dividing by the standard deviation for the respective distributions. Okay, so if one of them was spread out wide, when we divide it by that larger standard deviation, it's going to be now the empirical rule is going to be followed here with z-scores. Same thing with the with standard deviation for the y. Okay, so then we have an example of how we can use the regression to the mean. So the little hat here tells us a prediction, so we can predict the z-score for fat content based on using the correlation coefficient times the z-score for the x content. So if we have two standard deviations worth of protein, we can go up the 2 times the correlation coefficient, which would only allow us to go the slope of whatever that value is. I guess it's 0.83, so it'll be 0.83 times 2, which would be 1.66 standard deviations for the fat content. Okay, so basically the slope of the correlation, the slope of the standardized stat plot is going to be the correlation coefficient, which is where we get this whole idea of the regression to the mean. The slope is always going to be less than 1, so we're always going to back off our estimate closer towards the mean than what the original explanatory variable z-score was. Okay, so that's basically being displayed there. So if we divided by the standard deviations to get it to the z-scores, once we have the correlation coefficient, we take the sum of the products of the z-scores, right, to get the correlation coefficient. How do we then go from the slope of the standardized plot back to the slope in real world units? Well, if we divide it by the standard deviations to go back, all we have to do is take the slope of the standardized stat plot, which is the correlation r, and re-multiply it by the standard deviation of y divided by the standard deviation of x. If you think about it, when you have the slope, you're taking the slope times your explanatory variable, so you're dividing the explanatory variable to get rid of those units, and then multiplying it by the standard deviation of the response variable, which will change the units and convert it from grams of protein to grams of fat. Okay, so anyway, that's kind of what's going on here. So all we're doing is re-multiplying. Instead of dividing to get to the standardized stat plot, now we're multiplying it back to get back to the real world units of grams of fat per grams of protein, or grams of, yes. Anyway, so tale of two regressions. So if we're going fat versus protein, so we're going from the fat content, or so from the protein to the fat, and then over here we're going from the fat to the protein. So if you notice, the difference between these two is just we're switching the order of standard deviation y over standard deviation x, and look over here, standard deviation x over standard deviation y. So all we're doing is dividing, and the one on the bottom is going to be our explanatory variable. Our response variable will be on the top. And by the way, the response variable is the one that is going to be said first whenever you say like So it would be like y versus x instead of x versus y. In case you were curious, that's just standardly how they do it. So here's our summary stats that we have for the means and, more importantly, standard deviations and the correlation between those two variables. By the way, this is a good time to point that out. The correlation between two variables is the same regardless of if you switch the order, okay? So if we're finding the correlation from protein to fat, that would be the same if we did fat to the protein. The reason for that is, if you remember, this is the correlation is found, correlation is found by taking the sum of the products of the z-scores. So we'd have z sub x multiplied by z sub y, all divided by n minus 1. Well, does it matter if I change the order of z sub x and z sub y if I switch those two? No, because the product is going to be the same. If you do 2 times 1, that's the same thing as 1 times 2. So the correlation of protein to fat is the same thing as the correlation from fat to protein, which is really nice to know. So the correlation between the two doesn't matter which one you use for the explanatory and the response variable, but when you make the models, it does matter. So back over here, we're going to go from the protein to the fat. So basically, we have the protein on the bottom and the fat content on the top. Our correlation coefficient is going to be the 0.83 times the standard deviation for the fat content, 16.4, divided by the standard deviation for the protein content, which is 14. If we put all that in the calculator, which I'm going to do really quick. In fact, I think I already had it in the calculator. I did. It's going to be 0.97 and then some other decimals, whatever. And if we want to go from fat to protein, we're doing the same thing, except now we're switching the order of those. So it's going to look like this one here. So it's going to be 0.83 times 14 divided by the 16.4, which is going to give us the 0.785. So the next question you might have is, well, if we're just going from fat to protein and protein to fat, could you just rewrite the equation and work it backwards and find the inverse of the equation? Well, that is a good question. So what happens if I take this value here and I take it to the -1 power, which is going to do the reciprocal? Right? Well, when I do that, it's not quite going to be the same as the 0.972, but there's a way to fix it, and it's a clever way to fix it. So what happened? So I started out over here, and then I flipped it, right? So I put whatever is on the top on the bottom, and whatever is on the bottom is now on the top. So that's what I ended up with, right? But I need to instead, you see what's different between this one and this one? The R is on the bottom. So how do I fix that? Well, you can fix that by multiplying it by, if you guessed it, R, oops, not what I was trying to do, R squared, right? Because if I do R squared times the numerator divided by R, the squared is going to cancel out with the first power down here, so we're going to be left with just the R times S of X times S of Y. And to prove to you that that is the case, I'm going to take this value, which was the inverse of the previous one, and I'm going to multiply it times the correlation coefficient squared. And our correlation coefficient was 0.83, and then I'm going to do that squared, and that should fix it, and it should give me this number that you see right up here. I'm going to say that before it happens, so that when it does, oh my goodness, that's so cool. It is really cool. So you kind of can do it, but that's not really how you're supposed to do it. So just recalculate it, and we'll call it good. Okay, fun stuff. All right, so then the next thing is that we want to write the equation. So that's going to be the predicted y value is equal to the slope times x plus the y-intercept. Well, in order to find the equation for the y value, we would subtract the b1 of x. Oh, this is to find to get the y-intercept, the equation for the y-intercept. So what we're going to end up with is that b naught is equal to the y hat minus the slope times the x term. But we're going to evaluate this at the mean point, which is the 14 and the 16, or sorry, the 17.2 and the 23.5. So to do that, we end up with, so for our slope, we have the correlation multiplied by our response variable divided by our explanatory, which was a 0.97. And then over here, we can put that in the calculator if we really cared. And I suppose I do really care. So let me do that for you real quick. So to get the y-intercept, I'm going to do the y bar, so the average of the y, so 23.5, minus our slope, which we said was this value. I'm going to go ahead and just paste it so I have all that precision there, multiplied times the x bar, which is the 17.2, which will give me a y-intercept of 6.7 something. All right, so what I can do is I could actually put that value into the equation right here if I wanted to. So I'm going to do My slope, I'm just going to do 0.97. That's sloppy. I want more precision, but it's okay. You get the idea. That plus the 6.67, I think it was. All right. Anyway, so now it's stored as y3, and I can quit out. Yeah, 6.77. So let me fix that. So that 6.77. Now I could evaluate those if I wanted to actually like, if I wanted to put that in and evaluate for some value, which I probably will. Okay, cool. So here again are the summary stats for distance in miles and fares out of Atlanta, Georgia. Let me pull up the assignment real quick and make sure I'm looking at the right thing. Yep, that'll work. Okay, so they give us the summary stats. We have the means, standard deviations, and their correlations, which is what we need for today's stuff. What's the z-score of the cost of the destination? That's one standard deviation further than the mean distance. So what we're using here is the regression to the mean. So when we take a prediction, so our z-score, our predicted z-score for the y variable is going to be equal to the correlation times the z-score for the explanatory variable. So in this case, we want to find the predicted cost for destination. So the predicted z-score for the destination is going to be equal to the correlation of 0.694 multiplied by, we can put that in parentheses like that if we want, one standard deviation further than the mean distance. So I'm guessing that's going to be, yeah, further would mean a positive one. So that times 1. Well, that's easy. That's going to be just the correlation coefficient. So the predicted z-score for the distance is going to be equal to 0.694. And notice it's going to be closer than the explanatory z-score of 1 because we are regressing back to the mean by the strength of the correlation coefficient. Kind of cool. All right, what do we know about the mean and standard deviation of the cost to predict the cost of the flight in part A? What do we know about the mean and standard deviation of the cost? Okay, so for part B, if we actually know what the z-score is, now they want us to plug in the values to solve for the actual observation. So we know our mean for the distance is going to be 853.7, and then we want to add to that this many standard deviations above the mean. So we're calculating the predicted distance. So the distance hat is going to be equal to the mean plus the 0.694 times, which that's how many standard deviations, times our standard deviation for the distance, which would be 497.8. So then I'm going to put that in the calculator to get the actual final value. Quit out of that. Okay, so that's going to be 853.7 plus 0.6 4 times 497.8. Okay, so we're predicting that the actual distance is going to be 1,999 miles, and we'll just round it off to there. That'll be fine. Okay, cool. All right, what is the z-score of the distance for a destination that costs 2 standard deviations below the mean? So that's going to be a -2. So predicting distance, so z-score for distance, hat, is going to be equal to the correlation coefficient times the z-score for the cost. Yeah, so we're working backwards now, but it's totally fine. The formula that we use for the regression to the mean is exactly the same. We just switch the variables here. There's nothing else we have to correct. So the predicted z-score for distance is going to be equal to, and that's 2 standard deviations below the mean, so that's going to be a -2. So our correlation coefficient was 0.694 times -2 standard deviations below the mean, which is going to be equal to a negative, I'll just put that in the calculator real quick, not a big deal. So 2 times 0.694. All right, so -1.388. Okay, cool. Use what we know to actually find that value. So this is how many standard deviations we're going to go below the mean. So we are calculating the distance here. Okay, so from the mean distance, it's going to be 853.7 minus, because we're subtracting the 1.388 times the standard deviation for the distance, which we said was going to be 497.8. Okay, so then we can plug that into the calculator. which looks very, very similar to this one. Except a few changes. Okay, so that times 1.388 multiplied by the standard deviation. All right, there we go. So we're predicting the distance to be 162.8 miles. We'll do that. Okay. All right, moving on. All right, calculate the slope of the regression line that predicts the cost from the distance. So on this one, we're going to do the correlation coefficient. I'm going to do alpha x so that it shows it with the clear entry here. So that's going to be a correlation coefficient of 0.694 multiplied by the standard deviation of y, which is going to be our response variable, which is what we want them to be in, which is going to be that predicts the cost from the distance. So that would be standard deviation of the cost, which is the fare, which is 56.37, divided by the standard deviation of the distance, which is 497.8. Okay, so that's going to be your slope. And then we want to calculate the slope of the regression line that predicts the distance from the cost. So we're going to do the same thing. The only difference is we're going to switch the standard deviation. So now we're going to do 497.8. And then on the bottom, this is where we're going to do 56.37. Okay, now in case you were curious, once we have this actual value here, what we could do is take this, the inverse of it, and then multiply it by the correlation squared, which would, I'm going to put that in like this. So 0.694 squared, and that's going to give us the exact same value. Ready? Oh, so cool. Sorry, I did the mic pop there. All right, so are the slopes in part E and F the inverses of each other? No, because if we just did the inverses of each other, I guess I could show you that. So just the inverse of this one. Oops. So the inverse of that one is not the same. Yep, that is not the same as that. But if I multiply it by the correlation coefficient squared, then it would be, because that's how we fix it. So we fix it by multiplying it by the correlation coefficient squared, because that moves the correlation from the bottom to back to the numerator where it belongs. All right, example 2. Let's see if in statistics regression models can also be used forward and backwards. Hint, hint, we already know they can't. Enter the following measurements for 9 male subjects into the calculator list. So I'm going to put this in the calculator under stat and edit. I guess I still have all those lists, which is totally fine. But I'm going to go ahead and clear out all my lists. So in case you want to do that, you can do second memory, clear all lists, which is the fourth option, then hit enter. And then we'll go back to stat and edit. And I'm just going to put them in for list 1 and list 2. You don't have to name them. It's not a big deal. I'll pause the video and I'll resume it whenever I have it done. All right, so I have the waist length in list 1. In list 2, I have the weight. We want to sketch a scatter plot first, so we'll go to second y equals. If you notice, I have all of them off except the third plot, so that one's on. Do a scatter plot. My x list, sketch the scatter plot of the waist to the weight. So the waist was the list 1 that I put in first, so that would be second one. And then the y list, the response variable will be the weight, which is the list 2. I'm going to use, I guess I did red. It really doesn't matter what color you do. Anyway, then hit zoom 9. I'm going to have the y equal plots probably. Yeah, so I'm going to go ahead and turn those off. I always forget to do that. I don't know why I even put that one in there, because we didn't end up using it. But anyway, it's the same scatter plot there. Then the next thing we want to do is it appropriate to fit a linear model? So does it look linear? Yes, it does look linear. Do we have outliers? Not that I can tell. And then lastly, are we dealing with quantitative data? So is it actually appropriate to do a scatter plot in the first place? Yes. So we're good on all of these. It does not look like it's curved. It's actually linear. It doesn't look like we have any outliers, and we're dealing with quantitative data, so we're fine. All right, next we want to do is find the correlation equation for the best fit, the line of best fit. That's best fit line. I don't like how they say that. For the waist to the weight. So to do that, we go to stat, arrow over to calculate. The linear regression is the fourth option. Our X list, they are telling us we want to go from waist to weight. So that's going to be list 1, and then we'll do list 2. Okay, storing the regression equation just in case. I'm going to store it as y1. So variables, function, y variables, list one, then hit calculate. Boom, that's going to give us our correlation coefficient, which is what they wanted to know. So that's going to be 0.885, and we'll just round that, no big deal. Yeah, I guess if we did round it, it would be 0.886. That's what I wrote, right? Okay, fine, I'll just write it again. Okay, find the correlation, so that's what R is equal to, and the equation align the best fit. So you can write the equation by using the slope here, and because I'm lazy, that's how I roll. Because otherwise it doesn't show on the screen. So if I'm writing the equation, we're predicting weight, so WT hat is going to be equal to the slope of 3.9767, I'm going to round, times the weight, so no, times the waist, so I'll do WA, I guess, anyway, plus the y-intercept, which is going to be 38.19. We're going to call that good. Okay, cool. So that's my equation. I'm using weight and waist there. Use your model to predict the man with 37-inch waist. So to do that, the easiest way to do this, because we stored it in y1, is just to evaluate y1. So I'm going to quit out of that, go to variables, y variables. Make sure you know how to do this, because I mean, I know I show this in pretty much every video, but it is kind of the main thing you're going to be asked to do on the test. So that's going to be 185.3 repeating. So we would predict 185.3 repeating, and that would be pounds, I believe. All right, so we want to use algebra to solve the equation from question 2 for the waist variable. So essentially what we're doing is we're finding the inverse function, and so we're working backwards to switch the place of the x and the y. Okay, so to do that, the first thing we do is subtract 38.2 from both sides, so minus 38.2, and then we're going to end up rewriting it. So we'll have the weight minus 38.2, so there's a minus, is going to be equal to 3.98 times the waist, WA, okay? Then the last step would be to divide everything by 398. So this all divided by 3.98. So that would be our equation, in other words. So now we're predicting the waist hat is going to be equal to the WT. We can go ahead and actually divide the WT, do the reciprocal of that for the slope. Okay, and then minus 38.2 divided by the same value of 3.98. And you could actually write that as a new decimal and write that as a new decimal as well if you really cared, or you could just leave it in this form over there. It's all the same thing. So now we're going to use it to predict it as well. Oh, that's what it is. That's nice. I did the work for you. You're welcome. So use the equation from part D to find the waist of the man predicted to weigh 210 pounds. So we're going to put that value in there. So 210 multiplied by our new slope minus our new y-intercept, which will give us 43.11. So that's what we would predict. So that's not actually height. That should be the weight. Anyway, it would be 48.3 for the waist size. All right, now reverse the role of the variables to find the correlation of the equation align the best fit for the weight and waist using the regression data. So now we're going to go back and do it the way we're supposed to do it, which is in the calculator, calculating regression. This time just switch the list for list 1 and list 2. That's all you really have to do, and the calculator does all the work for you at that point. So now we're going from the waist to the weight instead of going backwards. I'm going to store this as equation 2. So function y2, and then calculate, and this is what our slope should be. Let me go back to what we had calculated, and we can compare that to what we have here. So our actual slope, it's all just clicking right over here. The actual slope that we should have used was going to be 0.19, where we had 0.251. So this is going to be way too high of a slope, because whenever we flip it, we're actually doing the reciprocal of the R value, and so again, you would have to multiply it by r squared to get the correct one. So that's why this is going to be so much smaller. In fact, let me test that theory just for fun. So if I did the 0.251 and then I multiplied that by our r squared, which I can actually get to the r because I ran a correlation by going to variables, statistics, and then the correlation is going to be the equation one. Yeah, here it is under the EQ equation. And I'm going to take that value and square it, and that should give me this value over here. Oh, sweet. So the only reason I had any difference between those two values, the actual one calculated and this one, is because this was a rounded off value in the first place. So I know it's stinking awesome, but then that value is going to change as well. The y-intercept is going to be different. It's going to be 0.4, so, and it's positive instead of negative. So everything changed. So you can't just solve for the equation by working backwards like we did here. That's not the way you do it. The way you do it is you put it in the calculator, you run another linear regression, and you just switch the list for list 1 and list 2. Okay, so what would that actual, we're going to redo that last thing that we calculated using our new model. So for 250 or 210 pounds, so I'm going to go to variables, y variables, function y2, which is our second equation, and I'm going to plug it in for 210, which will now be 41.86 instead of the original prediction, which was 43 point something. I don't remember. That's why you write it down. All right, so we did that, no big deal. Why are the equations in part D and F and consequently the waist measurements found for 210-pound man different? The reason they're different is whenever we take the reciprocal of the slope, the correlation gets put in the denominator, and so the way that we fix that is by multiplying the correlation by r squared, which is what we saw here. Once you multiply by r squared, that fixes the whole thing, but then also we would have to reevaluate the y-intercept as well. All right, what is the only and almost never true condition where the xy regression that solved for x gives the same prediction as the yx regression equation? So the only time that you wouldn't have an issue, if you think about it, is when the correlation is equal to 1, which that pretty well never happens unless, at least with real data, it doesn't happen unless we're measuring some natural phenomenon or something like that, like gravity. And that's it. We are done. I'm under 30 minutes, so that makes me happy. We will have one more lesson, I suppose, tomorrow, and then we have fall break. So I hope you guys enjoy your time off. Have a good one.